Okay, now that we've finished talking about comparing two proportions taken from two different populations, now we're going to compare taking means from two different populations. And so it's going to be the same as the first part of the unit, but now with the added complexity of comparing means instead of straight proportions. So this is what you're expected to be able to do by the end of this unit. Today's video will cover to about here. So last section we talked about comparing the proportions. What if we wanted to compare the means of population 1 and population 2? Our parameters of interest are once again mu1 and mu2, but we're not going to be able to find that. We're going to have to find x bar 1 and x bar 2. And we're going to have to try and make statements about how these relate to these. And so we'll take random samples from each population and compare the sample means. So we will have, a population of treatment 1 or population of treatment 2. We'll be able to find this. We'll know this, and we'll be making inference about that. So we can either take samples from two different treatments, or in an experiment we can have two different treatments. So this is what we see a lot. When we talk about when we're talking about experiments in Chapter 4, we'll talk about treatments in a controlled experiment. So we know that if we have one sample, we know the shape is approximately normal as long as the population distribution is normal, or the sample size is greater than 30 by the central limit theorem. We know the center of the sampling distribution is the true mean, and we know that the spread is the spread of the population divided by the sample size.
Howard, please go to the buses on the gym side.
Uh-oh.
Howard,
Someone's going to miss their bus.
the buses on the gym side.
Now, once again, we're going to run the trouble we had before, which is all this assumes we know sigma. So, to explore the sampling distribution of the difference between two means, let's start with two normally distributed populations. Based on information from the U.S. National Health and Nutrition Examination Survey, the NHANES, the heights in inches of 10-year-old boys follow a normal distribution with a mean, so that's mu, and that's sigma. So that's mu1, or we'll call that mu m, sigma m. And the girls, that's that's mu. That's mu f, and that's sigma f. So what can we say about the difference of x bar f minus x bar m? So first what we do is we take a whole bunch of samples from f, and we get an approximate sampling distribution of x bar f. This is a sample of 1,000 done on the computer, and this is an approximate sampling distribution of x bar m. And what we will see is that the boys are a little bit more spread out, but that makes sense because their standard deviation is higher. So the standard deviation of the sampling distributions is higher. Now, what do we think that when we do the next slide, will show x bar f minus x bar m, where we do one sample of each and subtract them and plot it. And then we do a sample of each, subtract them and plot them. We keep doing that again and again and again to get the sampling distribution. Well, what do we think that's going to look like? And remember, it's x bar f minus x bar m, so we would expect it to be 56.4, the center, to be the difference. But what are we going to do with the spreads? And sure enough, we get the difference that we expected. And the spreads, though, the standard deviation is actually increased. So why would the standard deviation increase? So remember, even if we subtract, we add standard deviations. Oh, I'm sorry. Ooh, I said something wrong. Even if we subtract, we add the variances. We don't ever add standard deviations. And so this was sigma f squared plus sigma m squared, and it's the square root of the whole thing. So what we will find overall is that the sampling distribution of one mean minus another mean, well, the center is the difference of the true means, and the standard deviation is the standard deviation of the first population divided by sample size plus the standard deviation of the second divided by sample size and the square root. And once again, this formula is given to you on the formula sheet. You'll find it there. Now, when data comes from two samples or two groups, right, we would say that this is the sigma right here. Sigma of x bar 1 minus x bar 2 is sigma 1 squared divided by n1 plus sigma 2 squared divided by n squared. Because remember, we're adding the standard we're adding the variances and then taking the square root to get the standard deviation. The independence condition is sampling, sorry about the bell, sampling less than 10%. Now, because we don't know the parameters sigma, we'll never know what sigma is. If we knew sigma, if we knew this, we'd know what this was and we wouldn't be messing with x bars. We're going to have to use the standard error and use the standard deviation of our samples. But as we saw, when we approximate the standard deviation of the population with the standard deviation of our samples, we get a different distribution. And that distribution is the t distribution. And we should have been comfortable with this based on so, and let me cover something up here. So this is our t distribution. The normal condition is met, right? If either the sample size of both sample sizes are greater than 30, or both distributions appear to be approximately normal, then the t value will be this. Now, remind you, our general hypothesis is going to be mu1 equals mu2. So right away, this is generally going to be 0. But how many degrees of freedom do we use? But to figure out the probability of a t-value, we need to know how many degrees of freedom. And before, degrees of freedom was n minus 1, but now we have two n values. So what can we do? Well, there's two different ways to attack this. If you're going to be using the textbook and the table, what you will do is use the smaller, do n minus 1, n1 minus 1, and n2 minus 1, and whichever one is smaller, use that as the degrees of freedom. But there is also a formula, which is this crazy formula right here, which is here, which gives a more accurate degrees of freedom. If you were going to publish, you would use this one. Because if you were publishing this formula will give you a higher number for degrees of freedom, which in turn will give you a lower critical value, which in turn will make it more likely that you'll either get a narrower confidence interval or a lower p-value. No one is going to ever ask you to plug numbers into this formula. This formula is a hot mess. But we will learn, the calculator will do that for us. And if you plug your data in, it will give you this number for degrees of freedom. And you are allowed to use that. So your confidence interval is going to be x bar 1 minus x bar 2 plus or minus t star and then the formula for standard deviation, the stat. And this is the same thing as we've always done, which is stat plus or minus critical value times standard deviation of stat. Right. And so all of this is given to you, and the t star is going to be the critical value for the confidence level of the t distribution with the degrees of freedom from either tech or the smaller of n minus 1 times n minus 2. And you can read through your section of the book and start looking at some of the problems. But otherwise, we will be creating these confidence intervals in class next time. So I'll see everybody then. Stay on it, guys. We really going to have to crank up the pace. All this snow has really slowed us down.